Hi friends, today I am giving a lecture on phases of a compiler or a compiler phases. So it is one of the most important question in compiler design. The phases of a compiler can be divided into these phases. So first one is lexical analysis, second one is syntax analysis, third one is semantic analysis, fourth one is intermediate code generation, fifth one is code optimization, sixth one is code generator, and seventh one is symbol table management, and eighth one is error handler. Okay. So here the compiler can be operated in phases. So each and every phase has a particular function. So these two phases, that is symbol table manager and error handler. Okay, these two phases belongs to each and every phase. So here the lexical analysis phase can also contain the symbol table manager and error handler. Syntax analysis phase also contains symbol table manager and error handler. Semantic analysis phase also contains symbol table and error handler mechanism. Intermediate code generator also contains symbol table manager and error handler. Code optimization also contains symbol table manager and error handler. Code generator phase is also contains symbol table manager and error handler. Okay, so the input for all these phases is source program. Okay, first we have to given a source program to the compiler. Okay, after the source program is processed through all the phases of a compiler, then it can produce the target program. Okay. Next, first we have to go to phase. That phase is lexical analysis phase. So the lexical analysis phase is the first phase of the compiler. Lexical analysis phase is also called as scanning. In lexical analysis phase, okay, first we have to scan the entire source program character by character. Those characters are formed as a stream of characters that is called as lexemes. These lexemes are produced as tokens as output of the lexical analysis phase. Lexical analyzer can do lexical analysis phase. Okay, here we have to write lexical analyzer. Here the phase is lexical analysis. That lexical analysis phase can be done by the lexical analyzer. In the same way, syntax analysis phase can be done by the syntax analyzer. Semantic analysis phase can be done by the semantic analyzer. Okay. Code optimization can be done by code optimizer. Code generation can be done by code generator. Okay. So in the lexical, the output of the lexical analysis phase is tokens. In the lexical analysis phase, the blank spaces between the characters can be eliminated during this phase. Okay. The input for the lexical analysis phase is source program. The output of the lexical analysis phase is stream of tokens. This is the description about the lexical analysis phase. That lexical analysis phase can done by lexical analyzer. The lexical analysis phase is also called as scanning. While reading the characters in the source program, if any blank spaces are there, that can be eliminated during this phase. Okay, while reading the characters of a source program, those characters that are read that can be formed as a stream of tokens. So that stream of tokens acts as the output of the lexical analyzer phase. Now consider the assignment statement. Position is equal to initial plus rate into 60. This would be grouped into the following tokens. So here position is one identifier, initial is another identifier, rate is another identifier. Okay, from these statement the identifiers are position, initial, rate. Next, equal to is the assignment symbol, plus is the addition symbol, star is the multiplication symbol. Here 60 is the number. Okay, so this statement can be formed as this one. Here when the lexical analyzer finds the identifiers position, initial, rate, that can be formed as tokens ID1, ID2, ID3. Here the token ID1 for position, the token ID2 for initial, the token ID3 for rate. Okay, so here after the lexical analysis phase, so this statement can be formed as ID1 is equal to ID2 plus ID3 into 60. Here ID1, ID2, ID3 are identifiers. So ID1 identifier refers to the position, ID2 identifier refers to the initial, the identifier ID3 refers to rate. Okay, now this statement after the lexical analysis phase can be formed as ID1 is equal to ID2 plus ID3 into 60. So this is the description about the lexical analysis phase. This is one example. Next, go for syntax analysis. Syntax analysis is the second phase of the compiler. Syntax analyzer can do syntax analysis. In syntax analysis phase, it groups the tokens of the source program and converted into some grammatical phrases. That grammatical phrases are used by the compiler to generate the output. This output can be represented by using parse tree. Okay, so this phase is also called as parsing. Syntax analysis phase can also be called as parsing. Here the input for the syntax analysis phase, whatever the tokens that are produced by the lexical analyzer phase, that are the input for the syntax analysis. What is the output of the syntax analysis? Parse tree is the output of the syntax analysis phase. Here the output of the syntax analysis phase is parse tree. The parsing can be done by parser. Here the parser converts the tokens produced by the lexical analysis phase into a tree-like representation called parse tree. Here, parse tree is the representation like a tree that is generated from the tokens produced by the lexical analysis. A parse tree describes the syntactic structure of the input. Whatever the input we have to given, for that input we have to represent the syntactic structure by using a tree called parse tree. Okay, suppose we can take the statement, so ID1 is equal to ID2 plus ID3 into 60. Okay, so this statement can be obtained from position is equal to initial plus rate into 60. Okay, so that can be represented by using a parse tree. So here assignment statement is equal to, okay, here identifier is position. Now this is the expression, this is the total expression for ID2 plus ID3 into 60. So this expression can be divided into expression plus this is also one expression. So this expression is identifier is initial. So here this expression is ID3 into 60. So this can be represented as expression into expression. This expression can be taken as identifier. Here the identifier is rate. Here this expression is number, that number is 60. Okay, this is the parse tree representation for the input string position is equal to initial plus rate into 60. Okay, so here the parse tree can also represented by using a tree called syntax tree. Here syntax tree is nothing but a compressed representation of parse tree. So in that one, the operator can be treated as interior nodes. Operands can be treated as children for the operator. Okay, operators can be taken as interior nodes. Operands can be treated as the children of the node operator. So for the same input string, position is equal to initial plus rate into 60. So the syntax tree is this one. So here the operators are equal to plus and into. So equal to plus and into are called as interior nodes. Interior nodes have some childrens. Interior nodes can be taken as parent nodes or root nodes. Okay. So here position is equal to initial plus rate into 60. Okay. This is the syntax tree for the input string. Position is equal to initial plus rate into 60. It is a compressed representation of the given parse tree. In this one, operators can be treated as interior nodes and operands can be treated as children for the node for the operator. Okay, so this is the syntax tree and this is the parse tree. Next phase is semantic analysis. So semantic analysis is the third phase of the compiler. Here the semantic analysis checks the source program for semantic errors. If any semantic errors are there in the source program, that are checked by the semantic analysis phase. Here it uses the syntax analysis phase. What are the operators and what are the operands are available in the expression and statement. So the main objective of semantic analysis phase is type checking. Okay, it checks each and every operator that has operands that are specified by the source language. Okay, it checks each and every operator that has operands. So that is called as type checking. That type checking can done by the semantic analysis. So for example, if a real number is used to specify an index of an array, for example, a of 1.5, okay, so this is an error. This error is semantic error. This semantic error is handled by the semantic analyzer in semantic analysis phase. Okay, it will be declared an error. That error is handled by the semantic analyzer at semantic analysis phase. So for example, it is assumed that all the identifiers of the statement position is equal to initial plus rate into 60. So this statement that are declared as an real, but 60 itself is an integer. All the identifiers here, position, initial, rate, are declared to be an real, but the integer 60 itself an integer. Okay, when here star is applied to be real, then the identifier rate and the integer 60 is also converted into real. This can be done while type checking is to be done. Okay, so during the type checking process, so then the identifier rate and integer 60 are converted into real when star is applied to be real. Okay, so here the integer 60 can be converted into real by using operator called int to real. So int to real, by using this operator, we are converting our integer into real number. Okay, so this tree is called as semantic analysis insert a conversion from integer to real. So up to this point, this is the same. This is the syntax analysis, but here the integer 60 can be converted into real by using a int to real operator. So here by using this operator int to real, the integer 60 can be converted into real, that is 60.0. 60 can be converted into real, that is 60.0. So this type of error is semantic analysis. This type of error can be checked in semantic analysis during type checking process. First of all, we are converting the identifiers into real, but the integer 60 is not converted. Now here the rate into 60. Suppose the star is applied to be an real, so the rate and integer 60 is also converted into real. But here 60 can be converted into real by using a operator called int to real. So by using this operator int to real, so it converts the given integer 60 into real number 60.0. Okay, this can be done during the type checking process at semantic analysis. The main function of semantic analysis is type checking. This can be done at semantic analysis phase. If any error is there, that error is called as semantic error. That semantic error can be handled during type checking process at semantic analysis phase. Next, we go for fourth phase of the compiler is the intermediate code generation. Intermediate code generation is the fourth phase of the compiler. After the syntax and semantic analysis, some compilers may produce or generate an explicit intermediate code generation for the given source program. Okay, that means for a given source program, after the syntax and semantic analysis, some compilers may produce an explicit intermediate representation of the given source program. The intermediate code representation of the source program has two important properties. First one is it is very easy to understand. Second one is easy to translate into target program. Okay, we can easily translate the intermediate representation of the source program into target program. The intermediate representation of the source program is very easy to understand. Next one is the intermediate code representation can be represented in so many forms. So one of the most important form is tree address code. What is tree address code? Tree address code is a sequence of instructions. Each and every instruction can have at most 3 operands. At most 3 operands is nothing but it may contain 1 operand, it may contain 2 operands, it may contain 3 operands. Okay, each and every instruction may contain at most 3 operands. Suppose we can take a given statement, position is equal to initial plus rate into 60. How we are converting this given statement into tree address code? So here tree address code means each and every instruction or statement contains at most 3 operands. Okay. So for example, this is the statement. So this statement can be converted into tree address code. So first one is temp1 is equal to int to real of 60. Okay. So in this one, highest priority given to into operator. So for that one, first we are converting the integer 60 into real by using int to real operator. So that is temp1 is equal to int to real of 60. Okay. Second one is after converting this integer 60 into real, it can be multiplied with the identifier rate. Identifier rate can be treated as ID3. ID3 into whatever the result we are getting, that is temp1. So ID3 into temp1, that can be assigned to temp2. So now we are getting this result. First, temp1 is equal to int to real of 60. That is the first statement. Second statement is whatever the result we are getting, that result is multiplied with the identifier ID3. Whatever the result we are getting, that result can be assigned to temp2. Okay. Next, whatever the result we are getting after this temp2, that can be added to the identifier ID2. So this result is ID2 temp2. Temp2 can be added with ID2. Here ID2 is nothing but initial. Okay, this result can be assigned to the variable temp3. Okay, now whatever the result we are getting, this is the total result is temp3. temp 3 can be assigned to the position. Here position is nothing but ID1. So here temp 3 can be assigned to the ID1. So each and every instruction can have at most 3 operands. So here 2 operands are there, here 3 operands are there, here 3 operands are there, here 2 operands are there. Okay. So these instructions fix the order in which operations are to be done. Here we have to fix the order in which operations are to be done. Next one is fifth phase of the compiler is code optimization. Here mission independent code optimization. Here we have to use mission independent code optimization. Here mission independent code optimization attempts to improve the intermediate code representation to get the better target code. Okay, we can get the better target code by improving the intermediate representation of the source program. That can be done by mission independent code optimization. In some compilers, the code optimization followed by intermediate representation to get the better target code. Next, the above intermediate code representation. Next, the above intermediate code representation can be optimized in these two statements. In the intermediate code representation, the first instruction is temp1 is equal to int2 real of 60. Second instruction is temp2 is equal to id3 into temp1. Okay, here the conversion of integer 60 into int2 real, that is 60.0, can be done all at once at compile time, so that that instruction can be eliminated. Okay, next one is final result temp3 can be assigned to identifier ID1. So this instruction is also eliminated. So whatever the result we are getting, that result can be directly assigned to ID1. Okay. The above intermediate code representation can be optimized into these two instructions. So first one is temp1 is equal to id3 into 60. Okay. So in the intermediate code representation, the first instruction temp1 is equal to int2 real of 60, that can be eliminated. Next one is, so temp1 is equal to id3 into 60. Okay, this is the second instruction in the intermediate code representation. By eliminating the first instruction, this is the second one. Temp1 is equal to id3 into 60. Now whatever the result we are getting, that is temp1. Temp1 means id3 into 60. This means is id3 into 60. Whatever the result we are getting, that result is temp1. This temp1 can be added to the identifier id2. Whatever the result we are getting, that result can be assigned to id1. Okay. So I will show temp1 is equal to int2 real of 60. Temp2 is equal to id3 into temp1. id3 into temp1. Next, temp3 is equal to id2 plus temp2. Next one, id1 is equal to temp3. So this is the intermediate code representation. So this statement can be eliminated because at the compile time all the instructions at once that are converted into real, so that this instruction can be eliminated. Next, this is direct instruction. So now temp1 is already, this instruction is already eliminated, so it can be written as temp1. Temp1 is equal to id3 into temp1. Temp1 result is directly 60.0. So therefore this instruction can be written as temp1 is equal to id3 into 60.0. Next one, this is temp1. Now we can take temp2. Temp2 is equal to id2 plus, here whatever the result we are getting, that is temp1. So that can be directly assigned, and this instruction is also eliminated because whatever the result we are getting at instruction 1, that can be directly assigned to id1. So these 4 instructions are intermediate code representation. This intermediate code representation can be optimized into these 2 instructions by eliminating this one and by eliminating this one. Only 2 instructions are optimized code instructions for the given statement. Position is equal to initial plus rate into 60. Okay. Next, go for last phase, that is 6th phase of the compiler, that is code generation. Code generation is the final phase of the compiler. In the code generation phase, so whatever the intermediate code representation of the instructions that are converted into some optimized form. Okay, so whatever the result we are getting at the 5th phase of the compiler, so that is the input for the code generation phase. So here the code generation phase converts the given intermediate optimized code into the target code or mission instructions or assembly code instructions. Okay, the code generation phase converts the intermediate code instructions or optimized code instructions, each instruction translated into a sequence of mission instructions or assembly code instructions. Okay, whatever the optimized code we are getting through code optimization, that can be converted into a sequence of mission code instructions or assembly code instructions. Okay, the memory required for each of the variables that can be assigned by the program. So the program can assign the memory for each and every variables that are used in the instruction. Okay, next, here for the given optimized code, so what is the code generation phase? Code generation phase generates. The code generation phase generates the target code for the given optimized code by using 2 registers, that is R1 and R2 registers. Okay, so in this one, the source operand, that is the source operand is this one. The source the first register, the first operand specifies the source. The second operand represents the destination. Okay, this is the source and this is the destination. This is the source, this is the destination. Okay, So in this one, F denotes the each and every instruction deals with floating point representation. Okay, first one is move F ID3 R2. Okay, whatever the ID3, the content of ID3 can be moved to R2. So now R2 contains, that is ID3. ID3 is rate, identifier rate. Next, multiply has 60.0 with R2. Okay, so now R2 contains, so rate is multiplied with 60.0. So now initially the register R2 contains only identifier ID3. Okay, now after the second instruction is completed, so hash 60.0, that is the converted real number 60.0 is multiplied with the identifier ID3, that is rate. Now the result is, so rate into 60. Okay, next one, move F ID2 comma R1. So now R1 contains ID2. ID2 is initial. ID2 is initial. Next one, add F R2 comma R1. So now R1 contains initial plus R2. Okay, initial plus R2. Initial is identifier ID2 plus R2 means rate into 60. So now move F R1 to ID1. So now ID1 is equal to, so initial plus R2. So that means initial plus ID3, that is the rate into 60.0. So the final result is there at ID1. So this is the ID1 is equal to ID2 plus temp1. So ID2 is initial, temp1 is nothing but rate into 60. Here the first one deals with the source operand, the second one deals with the destination operand. Here F means each and every instruction F contains that deals with the floating point instructions. In the above optimized, in the above target code, each and every instruction contains F. F deals with instructions or deals with floating point numbers. Next, hash 60.0 represents the constant. If the symbol hash before 60.0, then it can be treated as constant. Okay, so next one is symbol table management. So symbol table is a data structure that is used for storing the identifiers as a record. So here each and every record can be allocated for identifiers. Okay, next one is, so each and every identifier has some fields. In that fields we have to store the attributes of the identifier. Okay, so a symbol table is a data structure. In that data structure, a record is there for each and every identifier, and also some fields for storing the attributes of the identifier. Okay, this data structure allows to store the identifiers and to find any identifier so quickly. So that means to access the identifier as early as possible. For that purpose, we have to use this data structure. Okay, and also we have to store the identifiers and its attributes in that record. For that purpose also we have to use this data structure. So that means